Right, see if I can do this.
I don't know if that's a good idea.
There we go. How about that?
Good human factors.
I know, I don't think so. Good morning, campers. How's everybody doing?
Who's camping?
So, thumb sideways. Yeah, it's 9 o'clock. The caffeine hasn't hit the bloodstream yet, so we'll have an easy introduction. So tell me anything you remember from the past 2 days. Smushed effects. Yes, that's correct. What does a smushed effect mean?
If I got it correctly, when we assume that a level 1 predictor, we can just simply add it on a level 1 equation without having in mind that, of course, every level 1 variable also has a between person, for instance, cluster variance.
It also has a between part, exactly right. So smushing is the term that I use to describe a type of model misspecification in multi-level data where you put a predictor measured at the lowest level in without considering that it also should be part of the higher level. Yeah. Yes, sir.
I was wondering in an experimental context where you have trials nested in persons, and a level 1 predictor could then be like an experimental condition that refers to the trial.
It could be.
What about smushed effects there? Is it also a thing?
Is it also a thing? And probably not. So if you have trials that are administered in a random order, for instance, across participants, which is often the case, and you want to control for trial order, for instance, you think people might slow down or they might get bored or they might improve. In that case, trial order is purely a within variable because there's no commonality because you ensured that there wasn't. I think the same would be true depending on the stimuli. So if, let's say that you had only 4 different types of avatars, for instance, and you controlled for which type of avatar a person saw as a fixed effect, as a categorical variable, well then you've controlled for all of that higher level variance and you don't need to worry about it. So I think it could happen, but I think the design makes it so that you can probably avoid that just because of the way that you set up the study. What else do you remember? Or from 2 days ago even. I've got my partner in crime here.
I'm up here because I may have to present some.
I can't work a Mac, so he's my tech support to make sure that I can advance the slides.
Not just that.
Well, of course not just that, but that's why he's sitting right next to me as opposed
It's a bit odd, yeah.
you know, no, it's the show. What else?
We don't want to add shit up.
We do not want to add shit up, correct, except I totally am right now. But because you can't do everything you want at the same time, right? That seems to be a common theme from the questions I'm getting. It's like, I want to do this model and this model and this model all at the same time. It's like, well, yes, but not first. So, yes, we don't want to add shit up. Why not? It's easy.
Because we can't be sure that what we observed is actually a latent construct.
We can't be sure what we've observed would be corresponding to the latent construct. What do we assume about our items when we add shit up? Either one.
The parallel test model.
Yes, parallel items equal loadings, equal error variances, which translates into equal correlations. That could maybe happen in educational items, but at least in psychology type items, that...
No, it never happens in education.
It never happens then either?
No.
Oh, goodness. Yeah.
No, never.
It's a maybe dumb question. So you don't need to test for unidimensionality if you have parallel items because they're in itself?
No, you do.
It assumes it.
It's one of the assumptions.
Yeah.
Also, you have to test both.
Pardon me?
If they are parallel and if they are
That's right, exactly. If you think about it, if you take a confirmatory factor in a structured equation modeling software, and you encode all the loadings the same, all the residual variances the same, and you estimate that model, it is effectively testing with one dimension model fit. That's your test of the hypothesis right there. And I would be shocked, actually shocked. I'll pay euros to see a model that fits that, right? Because I don't think I've ever seen that with data in my life before. So, but that's what you assume when you add stuff up.
That's true.
Yeah, he doesn't want to say shit on the recording, but I don't have a problem with that.
I just read in literature computer exploratory factor analysis.
Pardon me?
I just read in literature that you should run an EFA.
No! It is not your
But
data's
that's
job to tell you what it measures, man. Like, no, like if you
Depend-
have a clue, right?
And
you start
depending on
thinking-
how you run it, there may not be an EFA. You just picked a different set of constraints. So
PCA is faster.
PCA would be faster, but is that really the same model is another question.
A principal component model is backwards, actually. The arrows go from the indicators to the component. So it's fundamental. It's more aligned with a formative measurement model, if you've heard that term before, where like the whole is different than the sum of its parts, which is not the same as this sort of thing. What else?
EFA is like ChatGPT 2, all right? It's like factor analysis 0.1, right? So,
How many chat GPTs are there?
oh, this is the 4th iteration.
Oh, I'm behind.
If you want the API, is it still only 3.5 turbo? So, anyway, yeah.
What else? Yeah.
An ICC of 1 means no within variance, ICC of 0 no within variance.
Yes.
And I was wondering because I heard that there are different versions of the ICC,
Yes.
and maybe you need to indicate which one. But I have the feeling that there's one overall ICC, which is referred to that 1 is no within and 0 is no between. But are there other ICCs?
There are many, many kinds. Yes, you are correct. I think the default when people see ICC in this multi-level sampling context is called ICC1. That's the one that I'm talking about. ICC2, which is given by some software packages, concerns the reliability of the cluster mean. And so if I remember correctly, it's random intercept variance over random intercept plus residual divided by n, level 1n, I think. It's probably close to that. In general, you can think of an ICC as a ratio of variances of some kind. So for instance, in generalizability models, so you can separate kinds of error to talk about kinds of reliability, absolute or relative. There's all different kinds of ratios you can build to get at what is true versus error. Those could all be construed as some flavor of ICC.
But usually ICC 1 is fine.
Yeah, I think ICC1 is the most important because it tells you at what level your variables are capable of having a relationship with other variables at that level. Right, what else? So this is multi-level model measurement courses. Am I talking about anything related to measurement yesterday afternoon? Probably not. So why are we doing this? As our son would say when he was 2, he used to say sometimes, "Mommy, why you are talking?" Good question. Why am I talking about this? How does this relate to where we're headed? Oh.
Anybody want a hint? Oh, we got a volunteer.
So what I find quite intuitive if you talk about all these kind of models, you start with LM, LMM, GLM, GLMM. So, and that's, for me, it was super helpful to learn these models this way. And I think you just have the building blocks to start.
Yes, building.
Multi-level, and then we go to measurement multi-level.
Yes, building blocks.
You teach us the measurement part.
I have a question for you to try to tie it together. First of all, what is the variance in school ability? So if we have our 10 items, math items, right? And students are nested within 62 schools. Do schools vary in their average level of ability for the math ability? And if so, how much of that variance can be explained by a student's proxy for how much income their family makes? Like free and reduced lunch. So
That would be our predictor.
does economic status of a student or the population of students at a school impact the average ability of the school in some way? So that's the question we're trying to answer.
So we're doing it with a sum score because that's easy and that's still common as a building block to eventually get to between and within latent variable models. So putting a within level measurement model, a between level measurement model, but all the same concepts apply. How much of the latent variable for maths variance is at level 2 versus level 1? Interclass correlation of latent variables would be able to tell you that. So that's where we're headed, is eventually trying to put it together, but doing it in pieces, because each piece could be useful to you on its own, right? If you do have a non-clustered sample and you want to do measurement models, there's plenty of people who do that. If you have an outcome that you either don't have the items or everyone in your field does it this way and you're going to use an observed variable, you can do multi-level modeling on that. All right, are there questions or things that after a semi-decent night's sleep you want to ask to clarify from before? Any topic.
If I'm not correctly mistaken, I heard ICC can be like beyond 1, 2, or did I miss?
There is ICC1 as a label for what we're talking about, and then there's ICC2 as a label for a separate type of ICC.
Okay, but the value itself is from 0 to 1 only. Okay.
Yes, because it's something over total, so it's constrained by 0 and 1. Yes.
Yeah, well, also practical question. So if I, for example, want to measure level 1 or level 2 variables, do you have any recommendation how I should put up my sample? So should I sample more schools and less pupils?
Oh, so
Because you said about
yeah.
this effective sample size we have.
Yeah, that's a very tricky thing. So in doing a study planning, your power to detect effects of predictors depends on the sample size at that level. So if you're interested in why some schools perform better than other schools, you need a lot of schools. If you're interested in why some kids perform better than other kids, you need a lot of kids. However, you don't have as many kids as you think you do because of the clustering. And so, like, ideally, if you wanted to eliminate the design effect, you'd get 1 kid per school. Now, that's a terrible idea and from a sampling perspective, but that would be, like, optimal. So every time you add more kids from the same schools, you're not adding as much of a child as you would think. And there are software packages that are available. There's Optimal Design. Can you think of the others? There's several different online calculators that can help you do the math as to, well, if I add 1 more school, or if I add 10 more kids for my current schools, like how does that shape out in terms of the impact on the clustering and the design effect?
And if you're able to do so, although that's a little bit more complicated, there are a set of tutorials on how to do models power through simulation as well too. Mm-hmm. So it's probably when you get into the situation of multi-level measurement model, you may end up in that area where you may have to just simulate to find power for the effects that you're looking for if you need it. Of course, then again, power in Bayes, we don't like to talk about that. Right?
Is that not a thing?
There's no p-values.
But you have a credible interval and you want to move it off 0. Is that not the same thing?
We come up, we just, we get off of that. And, yeah, I'm joking. It is still a thing. It's just not to the serious Bayesians.
Throughout my career, I've gotten to work on a lot of different grant applications in trying to do power analyses, and one that comes to mind was a very, very large study of students. It was supposed to be a cluster randomized control type of design, where they had schools that were control schools and they had schools that were treatment schools. And the overall sample was something incredible, like 10,000 children. But when you read how many schools there were, they were going to have 5 control and 5 treatment. And so I told them, this is terrible. Like, you have no power. What do you mean I have no power? I have 10,000 kids. Like, no, you have 10. Because that is the level at which the predictor would be for control versus treatment. And so I wrote a power analysis section that said something like, we have 80% power to detect effect sizes of infinity or greater, because that's what they were stuck with at 10.
Did it get funded?
It did. I think it did. I'm not entirely sure, but that type of conversation has happened more than once. So, anywho. All right, anything else before we dive back in? So we were talking about levels of variation. So the idea of starting with a naive guessing point, of giving each cluster, each level 2 unit, their own mean, which forms the basis of a random intercept. So the first model that we would estimate would differentiate how much variation is due to mean differences between clusters. That's our friend U, which is a random intercept. U's are always phrased as deviations. So fixed is like the center of the distribution. Random is how far off your level 2 unit is from the fixed. So random has a mean of 0 because fixed takes over what the mean would be. This has implications when you do it in Bayes because you might have a different prior for the fixed effect than you would have for the random variance around it, right?
And here's the thing about Bayes, nothing is fixed.
Right. I have to put fixed in air quotes, I think, when we get to Bayes. But the idea that it's a constant that operates in predicting everyone's outcome equally, I think, still holds as a concept. So after we have given each cluster their own mean, then we have the E's, which are the deviations from the cluster mean. So we're partitioning the total variability into two kinds, or two piles, as I like to say. There's between school mean differences, there's within school people differences. All right, we did the notation. So, any questions on notation? The multi-level notation looks unnecessarily cumbersome from the perspective of this model, but it starts to make more sense once you have more things going on, and it's an organizational system for keeping track of what predicts what. This just has 3 parameters, though. This is the ICC, so it tells you how much of your total variability is due to cluster mean differences. It also tells you what the expected correlation is of children from the same cluster, in this case. Did that. Design effect, how much more people you need to recruit because they come from clusters. Basically, that's an index of that problem. And then level 2 predictors. Level 2 predictors can be included in the regular way. So you would code categorical predictors so that some group is the 0, most usefully to me. You would constant center level 2 predictors so that the fixed intercept is meaningful at a 0 value. You can choose to do that or you can not choose to do that, and it really doesn't matter. It's just an interpretational thing. What I teach is literally from day 1 in regression, we center everything so that the fixed intercept stays meaningful. Where that will matter in these models is in entering level 1 predictors and giving them random slopes, which is what we hope to get to hopefully by break time, I think. All right, so effect sizes, pseudo versus total R-square. Pseudo R-square is per pile. So of the level 2 cluster mean differences, random intercept variance, how much did your level 2 cluster characteristics explain? When we add level 1 predictors, then how much of the within cluster kid-to-kid variance did your level 1 predictors explain? Putting it all back together again, if you generate a column of predicted values from your fixed effects, correlate it with the column of real values, that's R, square that correlation, and that's total R square. So there may be some debate about this. Why do you think I make a point of saying from the fixed effects only in capital letters? What if someone tries to add in the random effect into total R square? Could you do that?
I guess if you know the random effect of a given participant, for instance, of course this increases the precision of the prediction.
Yes. So yeah, every software package, for the most part, I think SPSS doesn't, but they may have by now, will also save a column of predicted U's. So they're not actual U's, they're like factor scores. They're estimates of central tendency of each person's distribution. But yeah, you can save those and add them to the prediction. And it would increase your R square. So the reason that I say not to do that is because I think it's cheating. Random intercepts are why are some clusters higher on average than other clusters? We don't know why. That is an error term conceptually. We know that some clusters are higher than others. We don't yet know why. So to include that as an R square, to me, doesn't make any sense. You haven't explained it. But there are people who do that, and it goes under the name of conditional R square rather than marginal R square, which is when you include the fixed effects only. So that is a thing in certain disciplines. I just don't think it makes any sense.
Question.
Yeah, sure.
How much of a difference does it make when, I mean, of course it depends on the analysis itself, but do you think that, or do you know that if we add these random effects in the calculation of R square, the difference is huge with and without them? So is it how big of a problem is this cheating?
Cheating is my word. Cheating is my word. I have opinions, right? I will give you my opinion, and you can feel free to agree or disagree. How big of a difference it would make is directly tied to the interclass correlation. So if your interclass correlation is 0.8, and then 80% of the variability is in the U's, and you add those U's to your prediction as explained, then you've explained, like literally from an empty model, 80% of the variance. But I don't think you have. You've decided that 80% is attributable to this reason, but it's still unexplained conceptually. If you had an ICC of 0.05, then it would make less of a difference. All right, others? Thanks for talking, by the way. We appreciate it. All right, then we get into level 1 predictors and what not to do. So every lower level variable, if you sample children from clusters, any child characteristic is likely partially a cluster characteristic as well. In a longitudinal context, if you collect data at different occasions, even though you're thinking of it as a day thing or a time thing, it's also indicating a person thing. So to the extent that we have, let's see, back up 1 second. Yeah, to the extent that for a predictor, so even though you're thinking of it conceptually as a predictor, for the purposes of figuring out what to do with it in the model, you also have to treat it as an outcome. Any predictor that has an interclass correlation of 0 can only show a level 1 within level effect because that's the only kind of information it has. That's pretty rare. Any predictor that has an ICC of 1 can only show a level 2 between relationship, and we would call that a level 2 predictor. Like that would be a pure cluster characteristic that is entirely shared across children from the same school. In longitudinal data, that would be something like, I collected a bunch of demographic information at baseline, I didn't ask it again, so it's shared across all the person's occasions. Only when the ICC is at those boundaries are you guaranteed to have only a level-specific possible relationship. If it's somewhere in the middle, it's partially level 1 and partially level 2. All right, so we did examples. Here's the terminology. So the fixed effect that results when you put in a level 1 predictor all by itself, and by the way, it doesn't matter if this predictor is constant centered. So you can subtract 3 or 5 or leave it alone. The problem is still there because subtracting a constant does not change the kind of information that it contains. It only moves it over in terms of what the values indicate. So this fixed slope right here, gamma 1O, is what I call the smushed effect, what other people call a conflated effect. And it assumes without testing that the level 2 between relationship is the same as the level 1 relationship for the parts of that level 1 predictor. So in terms of subscripts, by the way, this is gamma 1O because the 1 means I'm predicting beta 1. So in this multi-level modeling notation system, you get as many level 2 equations as you have level 1 betas. And so gamma 1O here is the starting point for how each cluster would get their own slope of this level 1 predictor, level 1x here. The fact that it's only this means that it's fixed. We're assuming without testing that that relationship is the same across clusters. And this is related to the endogeneity problem in other literatures, as I noted. So graphically, looks like this. So we have the within effect, the between effect potentially, and a contextual effect that we want to be able to differentiate. So you only need 2 of these to get to the third. That's going to be a common theme here. Depending on how you set up the model, you can end up with between and within. You can end up with within and contextual. But they are linear combinations of each other, and you can always get the missing one with respect to the fixed effects. So what we'll do this morning then is finish the idea of how different ways of setting up the model with respect to the level 1 predictor yield these different results. Okay, so the 3 ways then that we introduced last time. 2 of these are available in what we call univariate multi-level modeling. So the LME4 or NLME packages in R, the mixed packages in SAS, Stata, SPSS, trying to think of others. The HLM package, like the classic multi-level modeling routines, you have one column of data. The data are in long format where it's one row per level 1 observation, so per occasion in longitudinal data, per person in cluster data, and you're predicting only one column. So that means that any variance partitioning that you need to do with the predictors, you have to do yourself using observed variables as an approximation for what the model would do if you had an opportunity to predict another column. So that's what I mean by univariate. It's like one variable conceptually. In our case, the variable is just the sum score of math for each child. So you can either carve up the predictor into its level 1 and level 2 parts yourself and then put it in the model. This is what I prefer because you cannot screw this up. You can let the model do the carving up as a statistical control mechanism. This is more likely to be screwed up by beginners. Or number 3 is the latent variable analog to number 1. It's latent centering, or a multivariate approach, where you say, hey, can you take my predictor and create its random intercept and its residual variances in the same way that you did that for my outcome? So we'll show you all 3 of these as an example in LME4 and in Levon, and then Jonathan has the corresponding versions in Stan so that you can sort of build the model up piece by piece. And he has done some extra things in Stan to make it easy for beginners.
Well, let's be real. I don't know about easy, but
he created the equivalent of like the call to Elmer, like the model line that you just put your stuff in, and then magic happens through matrices. So that I can work with. All right, so cluster mean centering we started talking about before. Manual carving up process. So at level 2, we create a new variable that is the mean across people from the same cluster for that cluster, and we merge it back into the data. So this is CMX for cluster mean X. It has a C subscript because now this is a level 2 predictor. We've aggregated over all the level 1 units to create one level 2 mean as a variable, and you can center it such that 0 means something with a constant. So regardless of which way you specify your model, either cluster mean centering number 1 or number 2, that's your level 2 predictor. At level 1 then, we create a new version that takes the original level 1 predictor that still contains both the P variation and the C variation here, and we subtract off the C part. So then the new purely within cluster X is 0 if your value is your cluster's mean, like if you're average relative to your school. It's positive if you're higher than everybody else at your school. So it contains only relative information, which is okay because the absolute reference to what more than means goes in the model at level 2 where it belongs. Okay, how are we doing? Yes?
So sorry, I'm asking you about
No, please don't apologize.
I still feel like the level 1 part, that's clear because that's what we are also used to being called person mean centering.
Yes, same thing.
What we usually do with, like, not level 1, but with level 2 variables is we grant mean centering. But this is not grant mean centering. This is
not.
If I would, for example, say I measure my stress level over several days, then it would be the mean of a person across the days for stress.
Yes.
Minus what?
Oh, no, that's the minus part. So today's stress minus person mean stress is what this would be in longitudinal. This is kid X minus school mean X.
But what is then the level? I thought that the level 1 part would be then to say like my today's stress minus my usual average stress across the days. I thought this would be.
That is level 1. That's absolutely right in longitudinal.
And for the upper one?
Mm-hmm. The upper one would be my average stress minus some constant. So.
The constant is you said to make it more meaningful, but I'm still not
Yes.
getting that part, I think.
So let's say that you measure stress on a scale of 1 to 5.
Mm-hmm.
And mean stress might be something like a 3. Well, if I put mean stress on a scale of 1 to 5 right here, then the intercept in my model refers to somebody who has a mean stress of 0, which literally cannot happen on a scale of 1 to 5. So that's not wrong, but it's weird, because I like my intercept to represent someone who could actually exist in my data. So whether you choose to subtract off a 3 or leave it alone doesn't change your predictions or your model fit, but it changes the interpretation of your fixed intercept at a minimum. And if you were to fit interaction terms with this variable, then the interacting variable's slope would be conditional on a stress level of 0, which then is also weird because that can't happen. So at level 2, your only choice is to subtract a constant or not. Which constant that is just an interpretational decision.
Oh, I got it.
Okay, does that help? Okay, I've got a table I can fast forward to if you want to see like the math worked out, but I'm saving that for when we get to grand mean centering to try and contrast the two. Okay. All right, other questions or clarifications? Still with me? Okay, so if anyone needs to go get more coffee or biology calls, please feel free. I will not be offended. All right, so this is the way the model would work in the simplest case. So I've taken out any other predictors just to sort of focus on this idea. If I'm doing cluster mean centering, in purple is my new level 1 predictor that was made like this, level 1 minus the level 2 mean that goes with it here. It only has level 1 within variation, so its slope in the model, gamma 1, can only be the effect of having more than everyone else in your cluster. For every unit more X I have than my peers, right, than my school's mean, my Y goes up by that coefficient, mine. Not anyone else's, just mine. At level 2, the slope gamma 01 here, this is a level 2 predictor. It is the cluster mean of across children of whatever X is. So this is for every unit more on average that my cluster has than other clusters, my whole cluster's Y goes up by that much. So it's a overall effect. Everyone from that cluster gets that bonus in green there. And because these two variables were created to be uncorrelated or orthogonal, there is no competition between them in terms of what they mean. So you could put one in and its effect would be basically the same, or you could put the other in, or you could put them both in. So in this type of specification, I think it makes sense to put them both in at once. Because conceptually, the way that we think about variables and hypotheses is, let's see, I want to know if socioeconomic status matters. Well, okay, we're going to approximate that with free and reduced lunch. Matters means that it could matter at level 2 and it could matter at level 1, so I'm going to put them both in at the same time. And to the extent that whether or not you have more resources than everyone else in your school affects your outcome, the level 1 E variance should go down. To the extent that going to a school filled with more rich kids helps your school's mean performance relative to other schools, the U random intercept variance should go down. So they each have their own job to do in the model. So it looks like this then sort of conceptually. We have taken the overall level 1 variable that had some level 2 variance embedded in it. We've manually tried to distinguish that using observed variables. So the level 2 observed cluster mean that we create in our data set is an approximation for X of what the level 2 random intercept would be as a latent variable for Y. So that's why Y has circles and X has boxes, because at this stage X is observed, and for Y these are latent. And the within cluster deviation for a particular child then is an observed variable in this purple box, which is directly analogous to the level 1 residual for Y. So we've set up the model to be parallel on both sides. Just one way using observed variables and one way using latent variables. And if you're looking at this and going, why can't I use latent variables for both? You can. That's option 3. It requires a multivariate model where I can predict X with its own model, and I can predict Y with its own model, and I can let the pieces be correlated or have slopes between them as I wish. So you can do that in multi-level SEM software. You can also trick single-level structural equation model software into doing it. And of course, you can do it in STAN. Yes?
Oh, yeah. So that's, I think, super important. I just ask myself if you do a kind of exploratory approach, like I know step AAIC or so. If one, for example, the level 2 variable we created is not significant, is there any way of make our model more parsimonious, or would we smush our effects again if we drop out L1, L2?
So I think your question was like, if this between slope was not significant,
Yeah.
can we get rid of this box from our model?
Yeah, to make it more parsimonious.
Make it more parsimonious. Yes, you can. I don't think mathematically there's anything wrong with that, but to me it becomes weird. Because what you're saying is that at level 1, having more x than everybody else matters, but it doesn't matter how much you actually have, just more than everyone else. And what everyone else has is the level 2 reference. So I would tend to leave them both in to make the point that like what average is doesn't matter, but within school deviations do matter. But that's my preference. I don't think you would run into problems. Now you would run into problems if what you did was use this original combined predictor, because then you're back in smushed effect land. Okay, others. All right. So recapping then, this approach to specifying level 1 predictors, where we manually carve up their level 2 and level 1 variance into separate observed variables, directly gives us the level 1 within slope. The effect of having more of a predictor than everyone else in your cluster could explain level 1 person-to-person variability. The level 2 between effect of being from a cluster that has more of this person characteristic on average than other clusters could explain the level 2 random intercept variance. All neat and tidy, all nice and level specific. What it doesn't tell us directly is something that is often of interest in cluster data in particular. This is almost never of interest in longitudinal data. So if you only want to know about longitudinal, you can just go like this and say, I don't want to hear it, I don't want to hear it, because it doesn't matter. The contextual effect is the alternative version of a level 2 effect that may be of interest. It tells us to what extent the between level 2 slope differs from the within level 1 slope. That's one way to think about it. That's literally how we will ask for it in software. It also tells us, after controlling for the level 1 predictor's effect, what is the incremental additive contribution of the cluster. So if I am from a family with a lot of resources, maybe that helps my math score, yay for me. But does the school that I go to matter incrementally after controlling for my own status? Does it matter who my peers are with respect to their resources? If I go to a school where everybody has a lot of money, is there a collective boost that happens to everyone in my school, even the poor kids, because they go to that school? So it's after controlling for the individual, what is the additive contribution of the context? And that's where the term came from. So if you want to get that, the after controlling for version of the level 2 slope as contextual instead, then you can either ask for it as a linear combination from your previous model. And by the way, every software package has a way to do this. In R, I will use either GLHT for standard linear models and generalized linear models. In LME4, it's Elmer Test is an add-on to it that has Contest 1D. I'll show you how to use that. But every other package has a way to do this, and I've listed those as well. To get it directly as a model parameter, we change what goes in at level 1 to just use constant centering. We subtract 3 or 5 or 0. Leave it alone. The constant doesn't matter. And we replace the purely within version of the level 1 predictor with that one. So we're changing the information that is contained at level 1, which changes what happens at level 2. This is the tricky part. Now, why is that? Let me take a step back. Do you remember single level regression? When everything was nice and tidy and there was only one subscript, and It estimated in less than a second. Yeah, remember that? Wasn't that fun? That was nice. If I have a model that looks like this, I've got two predictors here, x1 and x2. If these two predictors are not correlated, then each slope represents its total bivariate relationship with the outcome, because they're not fighting over common variance. This is what would happen, say, in an experimental design, where you randomly assign people to one set of conditions, and then you randomly assign within those to another. So you've created these orthogonal factors, like in an ANOVA. Then that way, each has its own effect, uncontaminated by the other. Cool. What happens most of the time, though, is that these two are related. So if this is individual differences that happen to be related to each other, then we have to talk about it differently, because the slopes will differ depending on whether the other predictor is included. It then represents the unique effect that that predictor brings to the table after controlling for or additioning or holding it constant, like whatever phrase you learned. I like unique effect. So if you picture like your Venn diagram, it's discounting the overlap and it's only the part that's unique. This is the same principle that explains why you get different results at level 2 when you switch out what your level 1 predictor is. It's because of this change. They're fighting against each other. So here's a table that may help explain this. So let's say that I've got two clusters. I've got a cluster here for the top 2 rows and a separate cluster for the bottom 2 rows. And here are the scores for 2 people. So person 1 from cluster 1 has a 2, person 2 from cluster 1 has a 4. On average, that's a 3 for their cluster. Likewise, a 6 and an 8 have an average of 7. So at level 2, I might look at these and say, well, I'm going to center somewhere in the middle. Let's pick 5. So the first cluster has a level 2 predictor of -2. The second cluster has a level 2 predictor score of 2. Either way you set up the model, using cluster mean centering or grand mean centering as it is called, that same variable in green goes in. It's the same. Now your choice is what goes in at level 1. In this column right here, cluster mean centering, that's what I showed you first. This is where we manually subtract off the level 2 part. So this person is 1 unit below their cluster's average. This person is 1 unit above, and same here. So there's nothing in this column that tells us absolutely what the value of this variable is. It's only relative. I'm higher than my peers, I'm lower than my peers. It's only level 1 information. But in this column, if I don't subtract off the level 2 part, if we do what is often known as grand mean centering, because the constant you choose might be the sample's grand mean, but it doesn't matter what number it is. The principle is the same. This variable has only been shifted over. It still contains me relative to my peers, and my peers as a whole relative to other sets of peers. It has both. So in the cluster mean centering column, this WC purple variable is uncorrelated with the level 2 version, but over here they are correlated. And so when you put in 2 predictors that are correlated with each other, their effects change because they have to then capture the unique effect of that predictor. So here's what happens. So now this is a different version of the model. I would say this is more common in clustered data, actually. The original level 1 predictor goes in, perhaps centered at a constant, doesn't matter which one. And it still has all of its level 2 cluster between information and all of its level 1 within information. At level 2, though, we put in the cluster mean, and I've changed the color of it deliberately because now it contains a different effect in the model. It is the cluster mean. It only contains between information. So if you look at the information that is contained in these variables, what does level 1x bring to the table uniquely? What does it have that the other one doesn't? This is the audience participation portion of the program. What does it have? What does level 1x have in it in terms of its information that is unique to it that its other variable does not? Do they both have between information? Do they both have within information? They do not. Purple only has within uniquely, and so therefore it turns out to be the exact same within slope that we got from the other model, just through a different route. It's the within effect after controlling for the level 2 variability indicated by the other predictor. So either way, so long as you've got that cluster mean and at level 2, you're good. You can within cluster center to remove the variation yourself ahead of time, or you can not do it and let the model do it for you in creating unique effects. It works out to be the same. Okay, how are we doing? Yes, nodding. Thumbs sideways, halves. You can do parts. You can do like 45 degrees too. Question?
Can you say kind of practical example as well?
A practical example?
Yes, like with the rich kids, poor kids.
Rich kids, poor kids. Yes. So the example that we're going to do, and yes, someone would probably yell at me. You can't reduce people to rich kids, poor kids. It's hyperbole to make it work, right? We have this indicator of whether a child is eligible for free or reduced lunch, which is a marker of coming from a family with fewer resources. Okay. So rich kids, poor kids. So level 1 then is going to be the difference in the math sum score between children who get free lunch and those who don't, who go to the same school. Like a within school difference, because you have controlled for their school composition right here. At level 2, the cluster mean is the proportion of children who go to that school who get free lunch. Do you go to a school with no poor kids, or all poor kids, or somewhere in between? So after controlling for the status of the school at level 2 via cluster mean x, what is unique to the level 1 predictor is the purely within school effect, the difference between kids who get free lunch and those who don't in their math sum score. Turns out being poor is not helpful. Spoiler alert. Yes?
But that means if we have an ICC approaching 1, we won't see any effect. Because you can't see any within slope unique effect if you only have rich or poor kids.
That is true. That is true. So one of the things that we will do in the example in figuring out how much of the variation in math sum scores is between versus within, we're going to do the same thing with free lunch. We're going to treat it as a binary outcome in a logistic version of a multi-level model, but we're going to do the same thing. Because, yeah, that is a limiting condition. If we found out that all of the schools were completely homogeneous, then there literally is no variability at level 1 to do anything with. But to the extent that we have at least some schools where we've got poor kids and rich kids, then we have a chance to see that purple within slope. Exactly. Figuring out what kind of variance your variable has is a logical prerequisite to which kinds of effects it can show in your model. All right. So when all is said and done, even though we've swapped out which version of the level 1 predictor we have, its slope will be the same after controlling for the inclusion of the cluster mean of that level 1 predictor. Now, what's the other thing? As foreshadowed by the fact that I changed its color, this is the contextual effect. Because level 1x still has a little bit of between variation, this is the incremental contribution of that between variation beyond what would be expected at level 1. It is the effect of going to a school filled with more poor kids after controlling for whether or not you are poor. The contextual effect would apply to both poor kids and rich kids because it is a school level boost or decrement to their performance. So here's a picture. the way the model is set up, the level 1 predictor still has both sources of variability in it. That means that even though we're thinking of it as a level 1 within slope when we put it in predicting our outcome, it's also still predicting level 2 to some extent. And if we didn't have this blue box here, we'd be back to smushed effects, right? The purple slopes are the same. But we're going to unsmush it, yes, that's another term, by putting in this cluster mean at level 2 to carry the extra part that is not extrapolable, another word I'm making up, that is not anticipated by the level 1 predictor. And note that I have a double-headed arrow here to convey that these predictors are correlated. All right, so that versus that. All right? All right. All right? All right. Okay, questions? So this is what grand mean centering gets you. This is latent centering as option 3. Option 3 is let the model do it. Let the model partition the variability in X the same way that it does in Y. This requires multivariate software, multi-level SEM, single-level SEM, or some kind of Bayesian where you can do whatever you'd like. Here is a table from an article that was published last year. I wrote with a former student. It's called Catching Up on Multi-Level Modeling. It's an annual review of psychology. We had a lot of fun writing this article because we wrote it from the perspective of what if you're binge watching television during the pandemic and you find, I know, who would ever do that, right? You're binge watching television because you can't leave your house and you want to start watching a show that's in like its 5th season. Like, how do you get up to speed with what's going on? So we wrote it from this perspective of like chapter 1, chapter 2, you know, season 1, season 2. But this is a table that is in my book to some extent. It's labeled differently, but we put it in here as well. And this table illustrates why I say that cluster mean centering you are less likely to screw up. So the first 2 rows of this table describe model specification under cluster mean centering, or what more generally you can call variable centering because you're subtracting a variable. So cluster mean centering is conceptually the same as person mean centering or group mean centering, and rather than try to figure out what the right adjective should be, I just say variable centering. So if you do it that way, level 1 X only has level 1 within information. Level 2, the level 2 mean of level 1 X only has between information. Then if you put in the level 1 predictor without the level 2 version, you still get the within effect, and you're assuming that the level 2 effect is 0. So that was the situation at which you asked me about in terms of parsimony. Like, could you do that first column there? Yes, you can. That's what you're saying. You're saying there is an effect of relative information. There's not an overall effect of the context. If I did the opposite, if I put in only the level 2 mean of my level 2 predictor, but I didn't put the level 1 version in, then I'm saying, okay, what school you go to matters, but it doesn't matter beyond that, like your own characteristic. You're assuming it's 0. And if you put them both in, you get the same thing. So they mean the same thing regardless of whether the other one is included, because you set them up ahead of time to only contain level-specific information. Now let's compare that with the alternative. Constant centering, grand mean centering, meaning you subtract the same number for everybody. If you put in the level 1 predictor, that still contains both sources of variation, both levels, without the level 2 counterpart, you get the smushed effect. And what you're saying happens at level 2 is that is the same slope as the within slope, not 0, but the same. If you put in the level 2 mean without the level 1 version, it's identical to what you have up here. You get the between level 2 slope. And when you put them both together, you get yet a third set of possibilities, within level at level 1 and contextual at level 2. So even though the variable you put in at level 1, if I look at this last column here, is different, the level 1 slope is the same correct within slope. And even though the variable that you put in at level 2 is the same, you end up with a different version of its slope depending on which level 1 predictor it's paired with. And this, my friends, is why I have a job. I learned this so other people don't have to. And this table conveys why I say it's easier to screw this up. You really have to know what's in the model. And everything we've done so far is just main effects, right? You might want to examine moderation, interaction terms. Well, guess what? Interaction terms can be smushed. Yes. So if I have, say, a linear effect and a quadratic effect, I'd have to unsmush the quadratic effect. So it follows at all levels of model complexity that anytime you have a term in level 1 that has both level 1 and level 2 in it, you've got to control for the level 2 part by adding something else to your model. And it gets ugly real quick. All right. I don't know if I want to do random slopes yet. Yes, go ahead.
Maybe this is a very big question, but is it always really bad, or there are cases when it could be like that you get very similar results? So the smushed effect would always make your model like totally wrong, or sometimes it can be like ignored.
Great question. So to repeat for the recording, the question was, are there situations in which a smushed effect is okay? So I will tell you my opinion, and I will say that other reasonable people would disagree. My answer is no, it is not. Technically speaking, though, the contextual effect, another way to think about it, is the difference of the within and between. So if the contextual slope is close to 0 or non-significant enough, then what that says is that there is no extra contribution of the level 2 mean, and the information that the level 1 variable contains is enough, that the smushed effect is accurate enough. So on that basis, yeah, it would be more parsimonious to have 1 variable instead of 2. If the 2 slopes really aren't different, why not make them the same slope? The reason that I hesitate to say that that's okay is that it may not stay that way. So let's say that you put in your primary predictor of interest. It looks like the 2 slopes at level 2 and level 1 for between and within are close enough, so you put in the 1. Now what happens if you add other predictors? Well, the between slope and the within slope then become unique after controlling for the predictor. And the extent to which they stay equivalent, you would have to continue to evaluate, because at some point they may not be because of the other things that you've done to your model. Likewise, if you start fitting interaction terms, then these are conditional main effects, conditional on the interacting variables being 0, they may not stay the same. So I think because of that chance that you'd have to continually reevaluate that, and just for interpretation purposes, I think it's cleaner just to keep them separate and let it stay that way. That's my opinion. Okay. What do we have? I think we'll go ahead with this and then do the thing. 10 o'clock, we're still in there. All right. So when else might you want to do the constant centering for level 1 predictors? If you want contextual effects, if you want to know what is the additive contribution of the cluster beyond the individual. In clustered data, that is a thing. Then set it up that way, and that's what you get. If you have a categorical predictor like we have. So the first model that I'm going to show you is the constant centered version, because we're not going to center it. I have a binary variable of 0 means you don't get free lunch and 1 means you do. It's weird to think about cluster mean centering that. So if I have a cluster that, say, 30% of the kids get free lunch, then my level 1 variable would be 0 minus 0.3 or 1 minus 0.3. And that creates values that don't make any sense. So then my intercept is back to being like not a thing, because there's no children that would have a 0 for their level 1 predictor. So it's kind of weird, and people hesitate when they have categorical predictors to do cluster mean centering. I agree with that. So even though the variable is binary, the need to separate out its level 2 information from its level 1 information is still there. But because it's binary, it may make more sense to do it, just leave it as it is, and then you'll have within and contextual is what you get back. That's what we'll do. The third case is when you don't really trust the cluster mean. So the example that we have is actually a good illustration of that. What we have is student level data, and it's a subset of a larger data set where you've picked schools that had at least 50 kids, is that right?
Correct.
Yes. And 62 schools?
I think 62.
62, something like that. I know there's 3,100 people because there were 3,100 thetas that we had to do stuff with in STAM.
And I made it so that each school had the same number of children just to make a random sample.
So he made it balanced.
Yeah, just...
But what if you're doing a real study and you have certain schools where you're only able to get 3 kids? Are you going to take the average of those 3 kids and say, oh, that characterizes the whole school? That makes me uncomfortable. So if you're in that kind of sampling strategy where you might have supplemental data, maybe you get data from the district directly as to what the proportion of students who have free and reduced lunch is, right? It's an external source that maps conceptually onto the same construct, and you want to use that better, more cohesive and complete information, probably a good idea. But then cluster mean centering doesn't make any sense, because your level 2 variable isn't the cluster mean, it's this other piece of information. So in that case, I think leaving your level 1 variable as is and putting in that extra information at level 2 probably makes more sense. The other situation in which you, or let me say it this way, however, both of those things seem reasonable until you get to the bottom of the slide here. If you're interested in examining random slopes, which we have not yet seen. And by the way, we are not going to have random slopes in our multi-level measurement model because the thing's already been running for days. Weeks.
It was quicker yesterday.
It was quicker yesterday, but what was quicker?
A different parameter station.
I know, but like define quicker.
Oh, still a couple hours.
Still a couple hours. So yeah, this is a thing. But it is possible to do that in that context. But just so that you've seen sort of the complete picture. Any level 1 predictor so far has a fixed slope. It could also have a random slope in which the cluster gets its own version of the slope. And if you're intending to do that, then you should not be using constant mean centering. You should be using either the manual carving up so that it only has within information in an observed variable, or the latent version in which the model does it for you. But you need a pure level 1 variable to give the random slope to. Otherwise, you end up with a different kind of smushing. So what's a random slope? There's basically 4 combinations. I will show you in just a second.
So if we, for instance, have a categorical predictor that is an experimental condition 0 or 1, and we still want to see later on, for instance, some moderation, so we want to see whether it also works with random slopes, then you would say we still need to center it because otherwise it gets smushed?
Yes. I even though it's binary and it would make me sort of uncomfortable, I would do the cluster mean centering manual carving or the model-based latent centering. Yeah, because you need the pure level 1 to give the random slope to. I know, it's uncomfortable, but it's more correct.
Maybe not, because I think the part I don't understand is that I would say if it is, like it isn't within the same, so everybody has had the same zeros and ones, so there wouldn't be...
Oh, okay, that changes my answer then. So if you have a situation where it's a 0-1, like what happens on a day kind of thing, like what happened today, and everybody has the same number of zeros and the same number of ones because you've controlled it, then what's the ICC of that variable?
There is no between.
There is no between, correct. So what's the ICC? 0. So then if there is no between variability, there can be no between slope predicting something else, and you don't have to worry about smushing because your variable already is only level 1. So yes, thank you for that clarification. If you can control it experimentally, then that changes the answer. So if you have a level 1 predictor that has an ICC between 0 and 1, meaning it has at least some between level information, this is when you need to worry about it. All right, so what's a random slope? Each of these pictures assumes that the intercept is already random, so that part's the same. And let's say that x-axis here is my level 1 predictor, y is my individual outcome. The solid black line is like the mean across all the clusters, and the individual line would be cluster-specific slopes. So this picture is consistent with the model, in which the level 1 predictor has neither a fixed effect nor a random effect, because on average, it doesn't matter. There's no slope for x, and the no slope holds for all the clusters. So the lack of fixed is because there is no slope, it's flat. The lack of random is because flat works equally well for all the clusters. You could have fixed only. This is what our previous models have assumed, that the same slope holds for all the clusters, so there's no variation. And note that in each of these figures, you would expect homogeneous variance because there's nothing spreading clusters out differentially. That is not true in the bottom two. So you can have a fixed slope, or excuse me, a random slope in absence of a fixed slope. Maybe on average, the level 1 predictor doesn't matter, but in some clusters, it creates higher outcomes, and in other clusters, it creates lower outcomes. So finding a non-significant fixed slope should not necessarily stop you from looking for random. Like this could happen in a longitudinal study in an intervention design, where you have a control group that gets worse and a treatment group that gets better, and on average, the change looks flat until you dive in to the individual differences. So this is a much more interesting result, because then you have to try to predict, why is it that some clusters have a different slope than other clusters? This is yet another kind of variability to be explained with cluster level information. And you can have both. On average, there is an effect, and there may be cluster differences in the extent to which that level 1 predictor matters. So it's bad to be poor, right? I think we can agree on that. You're graduate students, you know this. It's bad to be poor. It's not helpful. Is it worse to be poor in some places than others? Probably. Is the gap between students who have free lunch and those who don't the same across schools? It's an empirical question at the least. It's a reasonable question. If you find at least some evidence that, yeah, it looks like it does differ across schools, then the question is why? How do we explain that additional source of cluster variation? So a model would look like this, going back to cluster mean centering. I've added in, yes, I knew I highlighted it, the yellow thing. That's my random slope. So this U1 is the deviation for that particular cluster from the overall slope. So if I have a slope that's positive and my cluster has a stronger slope, U1 would be positive. If my cluster has a weaker slope, U1 would be negative. So it's always phrased as a deviation because the middle that it's deviating from is the fixed slope. So you can have a fixed slope without random with it. You cannot have random without fixed with it. Fixed is like the baseline to which random is added. Even if fixed is near 0, I would keep it, because otherwise you're assuming that it's exactly 0, and that may not be the case after you continue building your model. So then this is purely within cluster information that's contributing to the slope for each cluster, which is what we want. The U1 just means that the extent of that slope differs across clusters. So we need to make sure that the level 1 predictor that this random slope is multiplying does not have level 2 information in it. A little bit more about that. What random slopes are sort of doing behind the scenes is introducing heterogeneity of variance as a function of that predictor. So adding a random slope implies that the variance across people with respect to that predictor is a quadratic function of it. So it's the variable squared times the random slope variance plus 2 times the variable with the covariance. So all these terms in the middle here are new. That means the extent to which children are correlated from the same cluster depends on their level 1 predictor. It introduces heterogeneity of variance and covariance. And if the level 1 predictor still has level 2 information in it, we are saying that the same pattern of quadratic heterogeneity of variance holds at level 1 as level 2. So it's like smushing, but on the variance side instead of the prediction side. So in this case, I would still not say that adding a random slope has explained anything. What we have done is take our original sources of variability that used to be level 2 random intercept mean differences, level 1 residuals, and we've taken out part of the residual and moved it to a new circle at level 2, which is a third pile, the random slope. Why are some clusters higher on average? I don't know. That's my random intercept. Why do some clusters show a stronger slope for the person predictor? I don't know. That's my random slope variance. Both of those are explained by cluster characteristics, and the latter requires something called a cross-level interaction. So that's the very last thing that I'll show you before we look at an example. So let's see. Yeah, that is how we figure out what terms explain what. Oh, did I take it out? No, I had a slide. Where'd it go? Okay, well, apparently I took that slide out. It is, let me go back. I'll show you what I wanted to do. There is a slide missing that I intended to be here where this term right here, do you see my cursor? Cluster mean X would go right here. What do you think its subscript would be for its gamma? Any guesses?
Gamma 1,
1, 1. Correct. And why is it 1, 1?
because it's a variation of the slope.
Because it's predicting beta 1. That's the first one. And the second one, because it's the first predictor of beta 1. So the 0 here is like the launching part for beta 1. The first predictor of beta 1 is 1, 1. If I added a second predictor of beta 1, it would be 1, 2. But 1, 1 is correct here. So that's what I wanted to show you, is the idea that perhaps the effect of being a poor kid depends on how many poor kids are in your school. That's what's known as a cross-level interaction, because it involves a level 2 predictor multiplied by a level 1 predictor. And the role of that cross-level interaction that would be right here is to capture this random slope variance. To the extent that the effect of being a poor kid is worse in schools with lots of poor kids, the U1 random slope variance would be reduced. So if I were doing pseudo R-square for this model, I would talk about how much the fixed effect of the level 1 predictor explained level 1 residual variance, how much the fixed effect of the level 2 cluster mean explained random intercept variance, and if I put this cluster mean right here as gamma 1, 1, it would explain this random slope variance. So each of these has a job to do. There. And then I had a bunch of stuff in case anyone asks any questions, which is bonus material, which I don't need to do. But here is my version of how you figure out which predictor explains what kind of variance and what kind of situation. Try to fit it all on one slide for your future reference. It's complicated, but you learn this, job security. Someone will pay you so that they don't have to learn it. The same is true for computer programming. And many other specialized skills. Doing taxes, right? We pay people so we don't have to do our taxes. Things that people don't want to do. All right. Questions? Yes, sir.
I don't know if it's too far, but I just thought of you could extract the random effects and you could compute confidence intervals for the random effects. And they're kind of more complicated because you see, for example, in certain groups you have a large within variance, and maybe the population mean is more reliable in this case and so on. Would you, if you now face a big school data set, would you exclude certain schools just, for example, based on, I don't know, the interval of the random effect is too large, and then I could run my analysis?
I don't.
It makes sense to have kind of this exclusion.
So are you talking about predicting a U for a particular school and then making a confidence interval around it?
It makes no sense to compute the group average. But for certain schools, but maybe it still makes sense if the school is in itself homogeneous.
Oh, okay.
Even if it's small. And that maybe could be shown by the random effect.
I don't think it would, because this model, let me back up here, we'll go back to this one. This assumes, without testing, that the E variance is the same in each cluster. Yeah, but you know what? We can fix it. So there is a family of models called location scale versions of mixed effects models. We talk about that in the review paper, where what you can do is build a linear model on top of the residual variance. And you can say there is more heterogeneity in schools that are of this kind and this kind and this kind. And you can do the same thing for U0. Maybe public schools are more heterogeneous than private schools, for instance. There's more variation among the public school U's than among the private school U's. So if you wanted to actually introduce that into the model, you could. Those models are also tricky to estimate, and Bayes is probably the best choice for those as well, unfortunately. I know, I keep coming back to, I need to learn Stan, damn it. That's one of the reasons why I'm not doing the Stan, is because he's teaching me it very slowly.
And I smush everything, so that's why she's doing the multi-level.
The random effects themselves, by the way, you will still see this in certain literatures where people output U's and they stick them in some other model. U's are factor scores, and they're likely to be shrunken because the U that you get is not the actual cluster mean. If you are from a cluster that is really far away from other clusters, or if you're from a cluster that doesn't have a lot of people contributing to its mean, it gets down-weighted and sort of shoved into the center, which is called shrinkage.
Can I add?
Yeah.
Why is it shrinkage?
Because the variability is shrunken?
No.
Okay.
It's a Bayesian thing.
Is
It's
it?
a prior distribution on U that shrinks it. Because U is distributed as a normal distribution, and that's a prior.
They're called empirical Bayes estimates.
And you were doing Bayes, and you don't even know it. It all comes back to Bayes.
Yeah, ideally, you do not want to output factor scores or U's and stick them in some other model, because what you're missing is the variability around them. Likewise, you don't want to output slopes as a variable and stick it somewhere else, because all the little residuals around the slope are gone and the slope looks perfect. So it's going to be optimistic. How to do everything at once, though, is where it gets tricky, and where multivariate and Bayes sort of can help you to not have to do these piecewise, two-stage kinds of things. All right, other questions? How about we do a break now, since we're going to change gears? Cool. Now we'll show you what happens to the poor kids after break in R, in LMA4, and then in STAN, sort of interwoven. How's that? Cool. All right, we'll see you in 10, 15, somewhere in there? That work? Okay, excellent.